Let's look at uniform distribution. In uniform distribution, this is another very commonly encountered distribution. Every time you go to casino, that's a lot of uniform distribution going on, or maybe not, right? So whenever we throw the dice with a six-sided face, that's uniform distribution 1 to 6 in a discrete manner because the dice has 6 discrete faces. So interestingly, however, the probability of any face occurring, we normally will say 1 over 6, right? But if we describe 1 as A and 6 as B, then B minus A, that's 5 only. So we got to add 1 back because we are counting the 1 itself, right? So that's those plus 1 and sometimes minus 1, they are there to make sure we count correctly. Yeah, so that is important in this case. But as we'll later compare with the continuous uniform distribution, then we'll find that there's a slight difference there. So uniform distribution, another very important class of distributions. This time we need two parameters, starting point inclusively and ending point, which is also inclusively. So we say the face, the face. That means when we throw the dice, the face is facing the ceiling. The face follows, the face is X, it follows uniform distribution from 1 to 6. The probability of any face showing facing upwards is going to be 1 over 6. Yeah, 6 minus 1 plus 1. Expected value, the mean value, when you throw the dice a lot of times, record down the numbers and find the average, that is going to be 1 plus 6, that's 7, divided by 2, 3.5. Now notice that expected value never will be shown by the dice because the dice will never show 3.5. And that you have to get used to it. So expected value is not necessarily on the sample space. Let me say again. Let's look at the right-hand side, uniform distribution representing throwing a six-sided dice. When we calculate the expected value, we will get 3.5. I hope you get 3.5 as well. Now, this 3.5 can nowhere be placed on the sample space because, truth be told, the sample space consists of 6 discrete points. It's not one continuous line. So it's the union of these 6 points kind of spaced apart. Whereas 3.5, no way to be found. Okay, so that's something peculiar, and I want you to kind of register that in a very stunned manner. What? You mean you cannot put the mean on the sample space? That's right. There will be no chance, no possibility that we will throw a dice infinitely many times and then suddenly observe a 3.5 showing up. Isn't it? Yeah, so that's why we cannot put the 3.5 on the sample space. So likewise for variance, we will likely get real number. So again, variance cannot be a number on the sample space most of the time, unless by chance, you get a variance of 1, 2, or 3, and then it will fall off. But that is, in general, not the case. So the variance takes up this rather lengthy form, and it's nothing spectacular. It's just following the definition of finding expected value of x squared, where x follows uniform from 1 to 6, minus the square of expected value, which is half a plus b. So notice that a lot of times we talk about expected value. When you put in words, it's just expected value, yeah? Just the words expected value. But it is confusing because you always must remember what is the distribution that x follows. If it is Bernoulli, it's called a different formula. If it's uniform, it's different formula. So you need to be clear in order to be able to solve problems. Question: where do we apply uniform distributions? Whenever we have equal outcome situation, equal chance outcome. So we know the outcomes, there are 5 of them, 6 of them, and we additionally, from domain knowledge, like we throw the dice, we know how the dice looks. So from our domain knowledge, from our expertise in this situation, we understand that the outcomes are equal, have equal chances. So then we will apply uniform distribution. When we have very complicated distributions, for example, like this, okay, so it's continuous distribution, it's maybe income distribution, whatnot, very, very complicated economical kind of situation analysis, uh, analysis of other scientific experiments, analysis of business observations, etc., etc. We will get into a situation where the whole curve is the whole distribution is very complicated, but we are interested in, for example, let's suppose this is income distribution. We're interested in the middle income segment of the population, right? So in this case, this curve itself may be very having a lot of wiggles and it's very complicated to describe it mathematically. We might just be contented with a rough approximation by just doing a horizontal line across and say, let's just use uniform distribution to describe this part. Yeah, okay, so that is what is meant by narrow interval. So for a small segment study out of a complicated big range of x values, we might just choose to simplify it by using uniform distribution. So that's possible. And finally, when we don't know the situation in front of us, completely no knowledge at all. No knowledge can be because the whole human mankind has no knowledge. That's one grand scenario, like COVID-19, right? When a patient gets COVID-19, will he or she uh, die in 7 days? Is it so deadly? So without further knowledge, we cannot really tell. But then we have to tell. So what do we do? Yeah, so that is the case when there are scientists who will debate and argue. But the fairest way, the most agreeable way out of no knowledge is perhaps just to use uniform distribution, where we say, okay, fine, let's begin with the notion that all outcomes are possible. The patient has 50% chance living, 50% chance succumbing to the disease after 7 days, let's say. Shall we start with that and then gather more data? Right, remember? So that's one approach. And that is a very favored approach. And you should take note of how this argument is being made here. Yeah. So when we have completely no knowledge, we will, without any prior data, then we will just begin with uniform distribution. Now, one more word. Although the example I use about COVID-19 is really, really that the frontier of human knowledge has no idea at all what is going on. And that's why it will be a very strong case where we say, let's begin with uniform distribution. That is very rare, right? So what about you and me, right? In the 99% of the case where we are not faced with a complete lack of understanding totally, then does it mean that we couldn't use uniform distribution? Now that the situation where we have no knowledge can be, of course, due to totally having no knowledge, or it can be that we at the moment have not enough patience nor time, right, to study completely well, or that it takes a long, long time before we are able to even understand a little bit more about the situation for our case, not about the rest of the experts, but for our case. So in this situation, for example, the company is deciding to invest in, um, uh, let's say Vietnam, a country that the company has no knowledge about at first. Of course, we can go and Google a bit, right? These days, we can always do some initial studies. But this company is, let's say, selling very niche products. And when you Google, you still also cannot find much information. Or if you find anything, you are a bit doubtful, right? So you kind of discard those that you find online. So what do? Well, we start with having no knowledge. So if you can imagine a debate going on within that company about the buying ability of the customers in this new country to invest in, then you might find that perhaps a good starting point is we don't know much. So uniform distribution. So all these are just to describe situations when we encounter the situation of having no prior knowledge that a fair way to begin with is all outcomes are equally likely.